Good afternoon. It's 1:30, so we are going to start the presentation. Philippe Edwards from Artelys and myself, Nicolas Omont, we are going to present Open RAO and the way we use it to maximize the exchanges of renewable energy, cross-border energy in Europe. So we have some time ahead, so we are going first to present the general context. What is capacity calculation? It's a general context about the energy markets. Then how the Remedial Action Optimizer works, Open RAO. And then we will deal with some non-functional aspects of it, its architecture, the technology it uses. And then we will illustrate it on a use case. So stay alive up to the end, because I think the use case shows the huge benefit it can have on cross-border flows.
So a few words on RTE. So RTE is the TSO in France. So we have multiple missions. Our most obvious mission is to operate the transmission system. So the transmission system is the high voltage grid, and our goal is to transmit the power from the producers to either the distribution system operators and also to some industrial consumers directly. A few words on our network. So we have over 100,000 kilometers of lines, and we have many cross-border interconnections. And we'll see later on why these cross-border interconnections are so important for us. Our other missions is to optimize the French electricity system and to inform public decisions with our experience and our knowledge.
So Artelys, we are a company specialized in artificial intelligence, decision support and modeling. So we are about 120 people. Mostly in France, but also in North America. We are specialized in numerical optimization, and we also do data science. We do software development, consulting, and in the consulting, we have an important part where we do energy prospective studies. We won't speak about that today. It uses the same kind of technology that as the one we are going to show, but it's to study to make energy transition plan, especially for the European Commission. So how the energy mix should evolve in Europe during the next decades. And today we are going to focus more on operational power grid computational modules that we are developing for TSOs, DSOs on power exchanges. So the general context is quite simple. So you've got the grid between France and Spain, Spain here and France on the top. And you see that you have a few lines that connect it through the mountains, not so many of them. So there is a western corridor, some lines in the middle, and an eastern corridor. And you want to send the maximum amount of energy. It does not always go in the same direction. So here you've got the exchanges for 1 day last year. And you see that it changes 3 times of direction during the day. So it's quite volatile. It depends on the economic activity in France and Spain. So France is having dinner at 7 p.m. and the Spanish at 10 p.m. So then at 7 p.m. the exchanges go in one direction and at 10 p.m. in the other one. So that's the kind of mutual benefits you have for interconnection. And then also more recently, it depends on the wind and the PV generation in France and Spain. So the thing is that you can optimize the grid, but the best grid optimization is going to change depending on whether you are importing or exporting. So it's going to change all the time. So you cannot do a study once and say, okay, this will be the optimized grid for the next 3 months. You really have to do it on a regular basis every day to adjust the grid to the conditions. And that's why you need a Remedial Action Optimizer, which is a tool that's going to select all the what we call the remedial actions that will allow you to maximize the transfers of energy between France and Spain. So we are speaking about topology measures. So that is how you can disconnect lines or change the way the lines are connected together into a substation. You can do redispatching, which is choosing one power plant in France and another one in Spain to adjust the flow. For example, if you have too much flow on the western part of the boundary and still some capacity left on the eastern part, you may choose to do a redispatching in Spain, where you will start a unit in Barcelona and stop one in the Basque Country. So that kind of very special measures. Or ultimately, you can do counter trading. That is, if you see that the exchange between France and Spain is not going to be safe, you just buy back, the TSO just buy back on the market what they have sold and say, okay, we thought you could send 2.5 gigawatt. Well, we don't see, it's finally it's not possible, so we are going to buy back 500 megawatt by buying some power in France and selling it in Spain if the exchange was from France to Spain. From Spain to France. And then there are two ways to use a Remedial Action Optimizer that are linked to the way the European market is structured. One is capacity calculation, and the other one is security analysis, or mainly, what we call ROSC now, but let's say grid operation. So, why do we have, well, first, who is from a TSO or from a RCC here? I think a lot of people here. Okay, so I'm going to go fast. So yeah, so in Europe, we have separated in 3 operations what in the US and in the US style market is only one step. So we have capacity calculation, market coupling, grid operation. So in capacity calculation, we are going to compute how much can be exchanged from France to Spain. So let's say in each direction 2.5 gigawatt. Then you do the market coupling. That is, you say to the market, okay, you're going to be able to do that, and then you take all the bids for generations and demand at the European level, and then you do market clearing, and that gives you the price of electricity in each country, but also the exchanges. So if the power exchange see that the price is low in France and high in Spain, it's going to use the capacity from France to Spain. And if it's in the other direction, it will use the capacity to export from low to high prices. And then in the afternoon, after the market clearing in the head, everybody is doing its work, and that in the end, we have a better forecast of what's going to happen on the grid on the next day. And then finally, here there were a lot of uncertainties. Here the uncertainties have been reduced, and the TSO may say, well, we thought it would be okay, and it's not going to be okay. So then you use another optimizer to find the least cost way to address the issues that you identify here. This is the ROSC, what we call the ROSC RAO. Whereas here we call it the capacity calculation RAO. So Open RAO is used for both steps, and to make it more complex, these 3 steps exist both in day-ahead and in intraday. So in day-ahead, you have these 3 steps, but for each intraday step, you also have a small capacity calculation, a small market clearing, and a small ROSC RAO. So it makes a lot of different places where you will use a Remedial Action Optimizer. So, Philippe.
Yeah, so now we'll give a few definitions. So the first definition is about capacities and overloads. So every network element has a maximum flow that it can transit. Basically, if you have too much flow on the line, your line is going to heat up because of Ohm's law. And when the line will heat up, it will expand because it's basically a big cable of metal. And as the line expands, it gets closer to the ground, and at some point it becomes too dangerous And so that's why we have a limit on every line of the network. Congestions can happen in two ways. So the first way, naturally, if you increase the consumption in one node, so you can see on the network on the right side, if you have too much consumption in one place and only a few lines to bring the power to that node, then the lines are going to be congested. So that's one case. So that was in an end state. And then also when contingencies happen, so when you lose a line, for instance, which wasn't planned, then all the flow which was being transited by that line will have to move to another line. And so in this case, all the power which was transited by the bottom corridor now goes to the top corridor, and so it creates a congestion. So this, we talk about n minus k states. So we have different kind of actions to solve congestions. So the first type are topological actions. So in this case, initially, we had one, in this substation, we only had one node. So here we have two lines connected to the same bus bar. And so it's as if the flows got mixed up together, and then they're redistributed on the two different lines. If you have some way to decouple the different bus bars, then you can have one line connected to the next line on the output, and here the same, one line connected to only one line. So now if each hour is 100 megawatts, for instance, here you had 800 megawatts coming in and 800 coming out, but with 500 at the top and 300 at the bottom. Here you have, once again, 800 in, 800 out, but you have decoupled the two bus bars, and so you have 400 megawatts on the top line and 400 megawatts on the bottom line. So that's one way to solve congestions. The second one is what we call linear actions. So for instance, PSTs. So we call them linear because the impact that they have on the network are additive. So it makes it easier to compute the impact of the different actions. This is complicated because it's topological actions, so it's non-linear, so it introduces many problems. So yeah, in the second case, it's as if a PST made it harder for a flow to go through the top line, and so it will prefer going through the bottom line. So that's another way to handle congestions. So as I said, the lines have limits because of the heat that's produced in the line, and the heat isn't produced instantly. The line doesn't go suddenly from, I don't know, 50 degrees Celsius to 80 degrees Celsius instantly. This means that if a line is overloaded, it can be overloaded for a certain time period before it becomes too hot. So this is kind of represented through this graph. So initially, you have what we call the permanent limit. So this is the limit which the line, the amount of megawatts that the line can transfer forever without causing an issue. Then we have an outage, which happens. And so we first go to the first temporary limit, which is the highest. This is usually around 1 minute to 5 minutes. So maybe it can support 130% of the PATR for 1 to 5 minutes, for instance. Then we will have a second temporary limit, usually 5 to 20 minutes. So it's a new limit, which is a bit lower. And then finally, it has to go back under the permanent limit. So to solve these different limits, we kind of have different kind of actions with different speeds. So the slowest actions are what we call the preventive actions. So these have to be taken a long time in advance. And so they are used mainly to solve the preventive congestions and the outage congestions. Because for the outage congestions, there's no other way of solving them. Then to solve the second TATR, we have what we call automatic remedial actions. Some of you know them as SPS, maybe. So these are actions which are not optimized and are not chosen by the operators. There are, for instance, PSTs on the network which will monitor the flow that go via the PST, and it aims to keep that flow at a certain level. So if there's too much flow on the PST will automatically change tap to reduce the flow. So these are very fast, which is why they are able to solve the second TATR. And then finally, we have curative remedial actions. So these are quite fast, but not as fast as the automatic remedial actions. And these are chosen by the operators. So these we also have to optimize. And so these are mainly used to go under the PHL at the end.
Yep. So the Open RAO is used on many capacity calculation regions. So what are the capacity calculation regions? They are linked to the coordination regions that we have in Europe. So you have seen many maps, I suppose, of the coordination regions. But I like this one because it shows that what makes a region is not a set of countries, but a set of boundaries. So each boundary goes in only one region. That's the key to understand it. So the SW region has two boundaries, France and Spain, and Spain and Portugal. The core region is, well, the big meshed part of the continental Europe goes from the Croatian boundary to Poland. And Italy North is a region in itself, just taking care of the boundary with northern Italy. And so for each of this region, for the two market frames, there is a capacity calculation. There is a market clearing, which is a single one for all Europe. And then so the ROS process is currently being set up. So it's not deployed on all regions. So right now, the day-ahead capacity calculation process is up and running with Open RAO on core region, SWE, and Italy North. Yeah, so now that we have finished with the context, let's see the methodology. So how Open RAO is working. So a RAO, whether it's capacity calculation or ROSC, is going to work with a base case grid model, so the famous common grid model usually, with CNECs. So if you like acronyms, so CNEC means contingency and critical network element and contingency. So it's a combination of an asset element, so a line or a transformer, and a contingency. So which means that you are going to check that there is no violation of the thermal limit on this network element after the given contingency. So this defines the security domain, and the list of available remedial actions. And so at the output of the RAO, you want another base case where you have applied the preventive remedial action. You need to give the remedial action schedule, so that is the list of remedial actions that have been chosen, whether they are preventive or curative, and also, of course, whether it succeeded, whether you solved all security issues, or whether it's still unsafe. So that's quite complex. And so why it is so complex? Because you have a lot of different remedial actions to optimize. Some are simple and some are not. So Philippe already mentioned some simple ones, which are phase shifter transformer, also HVDC set point, and basic redispatching. Why are they simple? Simple for two reasons. They are linear, so they are not combinatorial. You can model them with a variable that can take any value within an interval. And they are also additive, meaning that it's quite easy to model n-1 security constraints using sensitivity computation, or PTDFs if you want. So that's quite good because as we have seen yesterday, we can compute them very fast, and as Elia has shown yesterday, even faster if you use a GPU. So that's quite good. Then it can be a bit more complex. If your dispatching is a bit complex, you start to have unit commitment. That is units that can either be off or on, but when they are on, they have minimum power and that kind of thing. So that, and then it's time coupled also usually. So that is when they are started, they have to be kept running for a few hours and that kind of thing. That makes the problem combinatorial with a lot of integer variables. So that's already a source of complexity. And then there is worse. There are the topological actions. Okay, these ones are terrible because they are integer, but also you cannot use PTDF easily with them. So you need to recompute all the PTDF of the grid when you change the topology of the grid. So it's very, very painful. So that's why really everybody is focusing on this part because it's not tackled properly. So in Open RAO, there are special heuristics to manage that. And this is managed in a more traditional way with a linear optimizer. So then Philippe will explain you how it works in details.
Yeah, so for the topological actions, we basically use a heuristic, gluten heuristic. So basically we use a search tree, but we don't explore it completely, because if you have, for instance, 10 topologies, then you'd have to simulate 2 to the power of 10 different leaves. So it becomes very big, very fast. So what we do is we basically start with no topological actions at all applied on the network. Then we optimize the PSTs. So as Nicolas said, we basically use a mixed integer linear program. So in this case, for instance, after optimizing the PSTs, we get a minimum margin on of -15%. What this means is that the most overloaded line is overloaded by 15%. So this is the value which is interesting for us, and we want to maximize it as much as we can. So this is the first step. Then we basically develop this leaf by having 3 new nodes in the tree. So every time we will try applying one topological action and re-optimizing the PSTs, because we know that if we change the topology of a network, the optimal PSTs will change. So once again, at every leaf, we recompute the sensitivities of the different PSTs, and we solve a new linear problem. So in this case, we applied 3 different topological actions. In the first case, we actually increased the overload to 17%, so this is really not good. In this second topological action, we decreased the overload to only 3%, so it's almost secure, but not quite. And in the third, with the third action, we've decreased the overload, but only to 5%. So this is the best leaf for us, so this is one for now, which we're going to keep. And then instead of, for the second depth, instead of developing all the different nodes, we only develop the best leaf so far. So we keep this topological action, the second action, and we try apply the different actions which still remain to us. So the first and the third. So in this case, we get a minimum margin of 5%. So now this means that the most constrained line isn't even overloaded. There's still 5% margin. So there's only 95% of the capacity. We only use 95% of the capacity of the line, so that's very good. In this case, we also don't have an overload anymore. We have a margin of 3%, but this one is still better for us because we have more margin, so this is one we keep. We don't take into consideration the cost of the action in this case. And so you can see that this isn't, we don't find the global optimal because, for instance, we haven't tried applying the topological action 1 and the topological action 3. So to kind of solve this, we actually allow the TSOs to add combinations in the parameters because, for instance, maybe they know that they often use one action in combination with another, and so they can define in the parameters this combination, and so it will be an extra leaf with topological action 3 and topological action 1, for instance. So this is basically how we optimize the topologies, and for the linear actions, so PSTs and HVDCs, we use a linear problem. Then, as I said, we have different speeds of actions to solve different limits. And for this, as I said, we kind of assume that the actions defined for the different limits will be sufficient to solve a problem. This means that we won't, initially, we will only solve the preventive and outage instance using preventive actions. So this is the first step in our algorithm. the optimization of preventive actions, only looking at preventive and outage limits. So then in a second step, we basically have different contingencies which we try to simulate. And these contingencies are completely independent. The actions, the automatic actions and the curative action you'll take on one n minus k will be different from the actions which you take on another n minus k. So we can parallelize all these different calculations. So first, as I said, we simulate the automatic remedial actions. We don't optimize them because it's actually equipment on the network which will decide by itself whichever tap it takes, for instance, for PSTs, or whether to open or close a switch. The operator doesn't have a hand on it, so we can't optimize them, we can only simulate them. And then once we've simulated the automatic remedial actions, we optimize the curative remedial actions. So we do this for all the different contingencies. And then as a last step, optionally, we can re-optimize the preventive actions. For instance, we can find that after optimizing all the curative remedial actions, we still have one curative limit which is overloaded still. And so in this case, maybe by applying different preventive actions, we can reduce the flow on the curative limit. That's why, optionally, it can be useful to re-optimize the preventive actions. So when we re-optimize the preventive actions, in this case, we take into consideration all the limits. So the preventive limits, outage limits, automatic limits, and curative limits.
Okay, so so up to now we have described the RAO box. So you have seen there's already a pile of algorithms. There is a mixed integer programming at the bottom, then there is a tree search heuristic on top of it, and then there is this chain of computation for the different perimeter, preventive, and then curative, and the second preventive, okay? But now it's not finished. With this, we only have the margin that is left on the worst loaded line. But what we want is how much you can send from France to Spain. And in this case, well, that's quite simple. There is a dichotomy where you try to find, you change the export from France to Spain, and you increase them up to the point that the margin becomes negative. And then you say that it's your capacity. And well, this is the way to describe the dichotomy. And there are also some other checks that are specific to France, Spain, which are some voltage checks, because everything here, well, it's not possible to have voltage constraints inside the RAO, so some checks are needed. But apart from that, yeah, it takes what I said previously. Maybe I did not mention on the big picture the generation shift keys, which are very important. Especially for Spain, because of the disequilibrium between the eastern part and the western part, which can really change the way the flows are distributed on the boundary, depending on whether the generation is in Barcelona or in Basque Country. And well, and at the output, well, did not change from the previous slide. Yeah, so that just to illustrate a dichotomy. And we stop just to give an order of magnitude with a precision of something like 200 megawatts, or sometimes less. All this, you see, you have to compute it for three. You have four computation to do, because France, Spain, Spain, France, Portugal, Spain, and Spain, Portugal. So that's 6 limits to do, because the limit in one direction is not necessarily the limit in the other one. You have to do this for several timestamps of the next day, because the grid is not the same in the morning, in the afternoon, and at night. So that becomes a huge computation, and so it required to be distributed to be so that you can run it within the time limits. So somehow the longest computation takes, we will see that later, I think, but something like 40 minutes for one dichotomy. So then you have to distribute it to do it on many boundaries at the same time, and you could also do it for the timestamps. And so for that, we had to. There was a quite complex stack that was developed, to make it work. So everything is open source. It has been integrated into the PowSyBl library. So just here it's quite important. Open RAO has been open source for, I don't know, 3, 4 years, 5 years. It only joined PowSyBl last year. What does it change? It changed that now it is under the governance of the Linux Foundation NRG, meaning that the roadmap of Open RAO is discussed at the monthly steering committee in an open way. It was not the case before. Before, Open RAO was open source, but it was managed by Artelys. So that's why I want to say that there is a change here, because now somehow by doing this, Artelys is saying, I'm interested in external contribution, where it's not under the governance. It means that Artelys is not sure that they want to make to integrate external contribution. It has a modular architecture to import all that is needed. It relies on PowSyBl to import data and to import most of the data. And inside, you've got a load flow, which is PowSyBl Open Load Flow, but you could use other ones, any load flow supported by PowSyBl. You need a very performant sensitivity computation module. If you don't have it, if you don't have one that is able to use what is called the Woodbury matrix identity, then it's going to take ages to compute. So that's good to have open load flow for that. You use a MIP solver. Can be any solver supported by OR tools. So here I put FICO Express, which is not open source, that Artelys is using and Corezo is using operationally. It's possible to use, I think, CBC and a few other ones. But of course, it's less performant. And Kubernetes is used for the distribution.
Yeah, so we try to make something as modular as possible, so we can use many different breaks. So as we said, currently, for sensitivity computations are run with open load flow, but this can be changed to any load flow which is compatible with PowSyBl. For the MIP modeling, we use OR tools, which is open source. And so this allows us to use different solvers. So currently in operation, Corezo is using Express, but we can also use Skip or CBC. So then more technical frameworks. So we're under the Mozilla MPL 2.0 license. For the dependency management, we're using Maven. We're on GitHub, obviously. And we're using PowSyBl very much from network modeling to load flow computation. Using OR tools, we developed in Java because we were based on PowSyBl, so it made more sense using Java than anything else. For tests, we're using JUnit for unit tests, and we're using Cucumber for functional tests. I'll come back to this a bit later. So yeah, as I said, we can use different solvers, and soon, hopefully, in 2025, quite early in 2025, hopefully, you'll be able to use PowSyBl to run a RAO. This is our goal. We're quite happy with Sonar Cloud analysis of the repository. We require 80% coverage for any new pull request, and we're actually at 85%, so we're pretty happy with this. And so, as I said, for our tests, we're using Jenkins to run functional tests every night. So we actually have around 500 small functional tests on 12 node networks, which are on the repository directly on GitHub. So these are small networks which we created ourselves. So they're totally open. And so we add to these when we develop a new feature. And we also have, on top of that, some tests internally with real data. And for these tests, we usually populate it when there's a new bug, which which shows up in a process. We solve a bug, and we add the data in a database to run every night to make sure we don't break anything new. And so these tests usually take around 2 hours to run on the real data, and around 2 minutes for 500 scenarios on our open tests. So now we'll talk about use case, where we'll look specifically at the France-Spain border. So for this use case, we use data of SWE. So SWE stands for Southwest Europe. So it's France, Spain, Portugal. And so we used the data from the capacity calculation, and which is run daily by Corezo in the actual process. And so these tests we did just internally for ourselves to have values which we can present, but they are not part of the Corezo. It's not them who run the test, so it only really relies on us. So, yeah. So for the data, it was on networks that represent Spain, France, and Portugal. So there are 6,700 branches and around 4,000 voltage levels. In total, we have 18,500 limits which we evaluate. So this is on the product of the different lines which we evaluate at different instances with different contingencies. In total, we have around 100 contingencies which we simulate. We have 5 PSTs and 1 HVDC for linear remedial actions and 18 topological actions. So in this test, we only looked at the France to Spain direction because it was the one interesting on these dates. And for the dichotomy parameters, so the min value is 0 megawatts. We know that this will always be secure anyway. And the max value that is used in the process is 6400, because we know that we can't go above this, because we simply don't have the line capacity. If you sum all the lines on the border, then you can't exceed this. And so we stop the dichotomy once we've reached a position of 50 megawatts. So in total, there are 9 steps to run. So this is fixed because it's basically the dichotomy algorithm. And so for a processor, it's basically just my laptop, my work laptop, which I use to run the tests. So this is the data. The line which is the most interesting is the average, even if actually the gains are very similar between the different time steps. So on average, so with parameters, it's quite easy to either solve with no remedial actions at all, using only topological actions, using only PSTs, and using all the different actions available to us. In every case, we still simulate the automatic remedial actions, because this is a simulation, not an optimization, so we can't deactivate this. So yeah, these are really the actions which are optimized or not. So with no remedial actions at all, we usually get a max exchange between France, well, from France to Spain, of 2,000 megawatts. When we add either topological actions or PSTs, we gain another 200 megawatts. And what's really interesting is that we really need both topological actions and PSTs to really see an important gain on the exchange. And so in total, we gain 800 megawatts when we optimize both together. For the computation times, so yeah, you can see that PSTs, as we said earlier, is easy to simulate. It's additive. So adding them to the optimization doesn't change much on the computation time. However, adding topological action is the most expensive. So what's the goal of this? Why do we do this computation? Basically, if we look at the marginal prices of electricity, so the spot price, on the 2 timestamps which we played, so in dark blue, it's France, and in light blue, it's the value in Spain. So this is data which is published by the N3 transparency platform. And so this graph actually comes from the EIA website. So on many timestamps, there's a huge difference in price between Spain and France. This means that if we produce electricity in France instead of producing it in Spain, it will be much cheaper. So this is actually the values after computing the exchanges between France and Spain. This is why, in some cases, the value is actually exactly the same. It's because as you increase the production in France, the price is going to go up in France, and then you reduce the production in Spain, so you reduce the price in Spain in total. Hopefully, if there's no congestion, then the both lines can meet up, and this is what we see on several timestamps in the day. But there's still some big differences, so this is when the network is really, when there's really congestions, and so if we had more capacity, we'd be able to get the lines closer and exchange more power from one place to another. So then we did an estimate of congestion rate. So the congestion rate is basically multiplying the difference of price by the exchange value. And so we try to estimate what it would be using different type of actions. So for this data, we simply multiplied the results we got previously by the difference in price at the different instance. So with no remedial actions, just on 2 days, we can still have a congestion rate of 3.5 million euros. Adding either topological actions or PSTs, we reach 3.8 million euros. And if we combine both, then we go up to 4.9 million euros. So it's really important for us to be able to optimize both topological actions and PSTs in the same tool.
Well, we wanted to finish on these figures because we thought it was good to keep them in mind. It's just order of magnitude, and of course, it's not a study of exactly what the gains are, but it gives the idea of the benefits of using remedial actions on such capacity transfers. So now, I think we still have some time for questions. So, yeah.
So I have my questions around the optimizer, basically slide 17. So question one, like, what is the depth of the search tree that you use?
So he's asking what the maximum depth of a search tree. So this can be configured. Usually, we notice that on processes, we use usually between 1 and 2 topological actions. It's very rare that we go any further. And it also multiplies basically the computation time is multiplied by the depth, because every time we only develop one leaf, so it's linear. So I think in processes, usually it's configured to 5, the maximum depth, but we only usually go to 1 or 2.
So basically, like in, say, 2 depths, you are able to come up with a feasible solution that works, not necessarily optimal, right?
So yeah, he asked if with 2 it's optimal or if it's just enough feasible. So yes, definitely it's feasible. We only compute feasible solutions. We also stop as soon as we are secure. In the case of NTC, well, for instance, for SW capacity calculation, the process is called NTC, because we just check border per border the maximum exchange. So we're only interested in securing the network. So whatever happens, we stop, well, for this process, we stop as soon as the search tree finds a secure solution. So to answer your question, if it's optimal, we know that it's only an optimal locally solution, because, for instance, we didn't try topological action 1 and 3. However, if we were really, we can change the parameters to really maximize the margins and not stop when it's secure. In this case, we would continue developing the search tree until we reach a maximum depth, except if we can't increase the margin. For instance, maybe here we had one solution where the load would be 2% and 3%, and so we'd keep the solution, we wouldn't go any further.
Just one follow-up question on that. So is the business requirement to have a feasible solution or an optimal solution?
So yeah, is business requirement to be optimal or feasible?
Yeah. Anyway, this RAO is used either for capacity calculation or for ROSC. But in capacity calculation, you're going to stress the exchanges up to the point you don't find a feasible solution. So no, the objective is not to find a feasible solution. The objective is to maximize the minimum margin. This is all this RAO does. Then what you are doing with this piece of computation depends on the process. So capacity calculation, you just want the maximum transfer that is feasible. But for at least, given it's a dichotomy, you will have launched it once on a situation where the maximum margin was negative. And then you say, oh, it's too much, I go a bit lower. Yeah, so we are going to switch to the, maybe one question encore, but and then we can move on.
So, are you also considering voltage and reactive power coordination between the two TSOs?
I let Corezo to answer to this question. There are angle constraints on the Portuguese boundary, so reclosing constraints. So you have to make sure the angle is not too big.